Okay, so last one here is hydropower. All you need to know is that for hydropower we have a dam that blocks up water, builds up the gravitational potential energy of that water, all right, and then lets it fall through a set of turbines, spins them, and generates electricity. The easiest way is storing this in a lake. Another way we can do this is taking advantage of the tides and storing water that way, and then letting it through a dam after the tides bring it in. And the final way is pumped storage. If you pump the water at night when the demand is low, during the day you can let it fall through again when the demand is high for electricity. And that actually is a common thing that people do in certain areas, actually. So, all right, really quickly here we go from gravitational, all right, potential energy of the water, all right, to kinetic energy of water, and that kinetic energy of the water goes to kinetic energy of the turbines, and as always, spinning magnets in a coil goes to electricity. All right, final piece here, okay, as far as the equation that we care about. Remember, power is just going to be the rate of exchange of energy per time. So here we can say the rate of gravitational potential energy change per time will be our power that we develop. All right, so this is just going to be mg times delta h all over delta t. So another way that we can define this, actually, if we replace this is one possible definition that we will use. Another one is if we replace density times volume for mass, all right? And when we do that, okay, and we consider the flow rate over time, this delta V over delta T becomes the volumetric flow rate, and that we can give as Q dot, all right? Just a nice little variable for you to have. The dot means the derivative, so it's the flow rate there, the volumetric flow rate of water. Sometimes you're given as a variable, all right? So, okay, that's, the different variations of that equation there that we will end up using. So some examples of how you'll see this, all right? Here's the first one. We have some barrage, all right? It's placed at the mouth of a river at a tidal power station. So the barrage is 15 meters high. Water flows through the turbines, okay? And what we want to know is what is the power that can be produced if the power plant is 70% efficient. So what you do here, given the barrage height, I like to take half the height and say this is the average height, assuming this is perfectly straight here, okay? So the height that you're actually going to use, the delta H will be the average height. It's going to be 7.5 meters, all right? The flow rate of water, the total flow rate, in this case, is 500 kilograms per second because we have those 5 turbines each taking in 100 kilograms a second. So the power input that we care about, all right, coming from the water, is just going to be that flow rate of water times G times delta H, and we solve for this. We end up with 36.8 kilowatts. And since this is the total input, what we want is the useful output of electricity. And given that the plant is 70% efficient, it's going to look like this. So 0.7 times is 36.8. And what we end up with is 25.7 kilowatts. All right, that is our useful output power. Okay. So another example here, we have a reservoir. All right, that's 1 kilometer wide, 2 kilometers long. It's behind a dam. The top of this artificial lake is 100 meters above the dam surface. And the top of the intake is 25 meters below the lake surface. Okay, so what we want to do is calculate the energy, right, stored in this lake. In this lake that can be transferred into hydropower. Now, since we're wondering what the energy is that's stored in the reservoir, okay, I'm going to use this. Half of this is my height. Okay, explain why this is in a second. But first we need to find the volume. The volume, like we said, is these dimensions, 1,000 meters times 2,000 meters times 100 meters. And that is going to give us our 200 million cubic meters of water. So the potential energy, right, is going to be equal to the mass times acceleration due to gravity times delta H. And what we care about here is, the mass, calculating that from the density times volume. So 1,000 kilograms per meter cubed times this 200 million meters cubed gives us 200 billion kilograms of water. Ridiculous numbers to say. And there we go. This is how much energy is stored in this reservoir in terms of gravitational potential energy. All right. Now, because the top of the intake is 25 meters below the lake's surface, all right, we will not be capturing all of that. Instead, all right, since it's 25 meters below the surface, the average change in height, if we want to think of it this way, between here and here, that's at 25, the average delta H is only going to be, for that water, 12.5 meters. Okay? So, our delta H that we care about here is 12.5 meters. The volumetric flow rate is given here as 1 meter cubed per second. We know acceleration due to gravity. And what else do we have here? Oh yes, the density of water, which we'll need. Okay, so the power that can be generated here, and we're assuming 100% efficiency, of course, is going to look like the following, using this equation. And so 1,000 kilograms per meter cubed times 1 meter cubed flowing per second times the acceleration due to gravity, 9.8 meters per second squared, times the height, the average height that the water will have fallen through, 12.5 meters. And what we end up with here is going to be 122 kilowatts, effectively. So, actually with rounding, it's going to be 123 kilowatts of power. Okay? So there we go. Quick little example. A couple of examples actually for hydropower. And that's pretty much the level of problem that you're expected to do for IB for this stuff.